Whether you are predicting customer churn from a spreadsheet or training a massive language model, the core learning mechanism remains exactly the same. They both rely on a continuous loop of 5 specific lines of PyTorch code. Today, we are going to write those 5 lines from scratch. We will build the PyTorch training loop and see exactly how it physically updates a model's weights. Before we start, we already have our basic neural network defined using nn.module, and our training data is divided into manageable batches. By mastering this single repeating loop, you secure the mechanical engine required to train any modern deep learning architecture. Before we enter the loop itself, we have to establish the rules of the game. That means defining our loss function and our optimizer. First, we set our criterion. For this binary classification task, we are using BCE with logits loss. If your model outputs raw, unconstrained numbers, known as logits, feeding them directly into a standard binary cross-entropy loss will crash your training with numerical instability. BCE with logits loss safely combines the required sigmoid activation and the loss calculation into one mathematically stable step. Next, we set up our optimizer. We will use the Atom algorithm. We configure it with a default learning rate of 1e to the -3. This rate dictates the exact size of the steps the model takes when correcting errors, serving as the most reliable starting point for tabular datasets. With this setup complete, we have created our compass to measure exactly how badly the model is failing and the engine to drive its improvement. Now we start the iteration. Line 1 is optimizer.0grad. Every batch, we zero out the old gradient data. If skipped, PyTorch doesn't overwrite gradients, it adds them. By batch 10, your model takes wildly oversized steps in the wrong direction, acting on stale data. Line 2 is the forward pass. We feed the input batch in to generate predictions. Line 3 calculates the loss. We pass those predictions and the correct answers into our criterion. This terminal readout shows the output of that calculation, a single scalar value measuring exactly how wrong the model is on this specific batch. Line 4 of the loop triggers the analysis, loss.backward. This commands PyTorch's AutoGrad system to trace backward through the computation graph. It calculates the exact share of the blame for that total error and attaches a specific numerical gradient to every single parameter. These first 4 lines perfectly diagnose the network's mistakes. To complete the cycle, the system actually has to fix them. Line 5 is optimizer.step. This is the moment the physical change happens. The optimizer takes those newly calculated gradients and directly adjusts the values inside the model's weight tensors. This visualizes gradient descent. The model evaluates its error position on the curve, seeking the lowest point. The learning rate restricts how far it steps down the slope. Set too high, it overshoots, bouncing out of control. Set too low, steps become microscopic, stalling training. Without this 5th line, the network knows exactly what it did wrong, but it remains completely incapable of learning from it. We assemble these 5 lines in sequence, nesting them inside a standard loop to iterate over every batch in our data. We execute the cell, and the automated training process begins. This animated curve tracks the optimization process, showing the loss integer physically dropping batch by batch and epoch by epoch as the model successfully learns. This exact loop architecture is fully functional and production-ready for real-world tabular data. Because the model can now continuously update its weights and memorize its training data, our mandatory next step is proving its accuracy on unseen validation data.